You click a button, a loading wheel appears, and your entire screen locks in place. The system is completely frozen. Deep in the system, two digital processes are trapped in a deadlock. Process A needs a piece of memory held by Process B, and Process B refuses to let go until it gets what Process A is holding. They will wait for each other forever. While it might seem like a flaw the operating system should have caught, this state is often a deliberate design choice. The system is fully aware that deadlocks occur, but it chooses not to stop them beforehand. Anticipating and blocking every potential collision takes an immense amount of processing power. If the operating system meticulously checked every single resource request for potential loops, overall efficiency would plummet. To preserve raw speed, the operating system allows these risks. It functions through a strategy of continuous monitoring and decisive post-error intervention. This diagram shows how the operating system tracks that chaos. It's called a Resource Allocation Graph. The glowing circles represent active processes, and the rectangles represent the resources they need to function. Arrows connect them to map out the exact dependencies. An arrow pointing from a process to a resource means the process is requesting it. An arrow pointing back the other way means that resource is actively assigned. To find out if processes are waiting indefinitely, the system strips away the rectangles. This leaves behind a simplified map called a wait-for graph, drawing direct lines between processes that are stuck waiting on one another. The operating system scans this entire web of dependencies, looking for a specific mathematical flaw. Do you see it? Right here. Process 1 is waiting for Process 2, and Process 2 is waiting for Process 1. They form a closed loop. The moment the algorithm confirms this circular dependency, the operating system pivots. It stops passively monitoring the traffic and prepares to execute a recovery protocol. If the cycle isn't broken quickly, the freeze will cascade, starving other processes of the resources they need to function. One recovery method is process termination. The operating system instantly kills every process involved in the deadlock, destroying uncompleted work to clear the loop. If wiping out all that progress is too costly, the system takes a surgical approach. It calculates which process has the lowest priority or the shortest execution time and terminates them one by one until the path clears. Instead of terminating a process entirely, the operating system can use resource preemption. It forcefully evicts a process from its current memory or hardware assignment, handing those resources over to someone else. But preemption has physical limits. If you forcefully yank a hardware assignment away from a printer halfway through a job, the output is permanently corrupted. To handle safe preemptions, this execution timeline shows the system using a rollback technique. When a resource is stripped away, the process is rewound to a previously saved checkpoint, pausing safely until the resources become available again. These recovery tactics inevitably destroy work and sacrifice individual processes. The system actively trades the survival of a single task to ensure the macro environment stays alive. In massive server architectures driving modern enterprise databases and cloud networks, this exact detect and recovery sequence executes thousands of times daily in the background. Because true deadlocks actually happen very rarely, burning constant computing power to prevent them is economically irrational. Software engineers recognize that trying to build an error-free environment chokes a network's potential. They stopped building preemptive walls and started optimizing the system's ability to recover. This architectural choice dictates that a highly functional system is one that prioritizes extreme adaptability over absolute security. Digital resilience is defined by the speed and ruthlessness of the recovery. In these massive architectures, the strength of the system lies in its ability to survive its own inevitable failures.